Welcome everyone to Joseph's PhD defense. I am delighted to introduce Joseph. Joseph has joined our research group coming from Colombia. He worked in our research group with a really interesting idea that built on his EE interests. For his master's degree, he developed a robot compiler that allowed users to specify the function, the electromechanical function of a robot at a high level, and then all the electronic designs required to deliver on that function were done in the background as part of a compilation process. Joseph applied his great interest in robots, electronics, and programming to many projects in our lab. He was instrumental to the development of Sophie, our soft robotic fish. And in that project, he also worked on an interface that allowed users to program or to task the robot from the distance, but in an acoustic medium, using a special language, a human understandable language. So you can see a theme here. Since the very beginning of his PhD, Joseph has been interested in more intuitive and broader interactions between people and machines. And for his PhD, he took that broad question and dove into deeper details, looking at how to get robots to be controlled as minions, sidekicks, and apprentices. And his PhD dissertation tackles just that. It's been a great joy to have Joseph part of our research group. Joe has been always ready to lend a hand when a new problem needed solving, always ready to jump into a brainstorming session, and generally a kind of presence in the lab that has provided everyone with great technical conversations and also fun social interactions. And so I'm very eager to hear Joseph's thesis work summary in this talk. Joseph, please take it away.
Thank you, Daniela, for that very kind introduction. And thank you everyone for coming. I'm excited to tell you about our work on using wearable sensors for more plug-and-play human-robot interaction. In recent years, robots have started to become more common, especially in places like research labs, factories, and medical settings. And these applications have showcased how robots can help enhance our capabilities and improve productivity or quality of life. But when we imagine a future of ubiquitous robots, we also think of more personal robots, assistants or companions that are intuitive and multi-purpose. They're as easy to use as an app on your phone and can give both physical and computational support. So what are the challenges to having more robots like these? Well, one barrier is that it's hard for robots to know what people want them to do. And this is especially true in unstructured environments that the robot hasn't seen before. So two pieces for bridging this gap are communication and adaptability. Basically, how do we tell the robot what it should do? And how should it apply that in new circumstances? So first we could think about communication. And we can imagine a spectrum of possible ways that we might want to interact with the robot. On one side, we have robots like C-3PO from Star Wars that you can talk to as if it were another person. And on the other side, we have robots like the Iron Man suit that use direct physical contact and biosensors to infer intentions. And even in our reality, there's been a lot of great work throughout this spectrum. So combining benefits from all of these modalities will ultimately help bring us closer to these futuristic robots. But for the current thesis, we'll focus on using wearable sensors and biosignals. And we'll aim to use these in a way that lowers the barrier to casual users interacting with robots. So being wearable means that the users don't need to set up sensors in their environment and don't need to worry about avoiding occlusions or workspace bounds. And biosignals in particular can help detect physical states like stiffness or cognitive states like noticing when a mistake is about to happen. And they can often do this unobtrusively to allow the person to perform the task as they normally would. Then we'll also use these properties to develop algorithms that reduce computational demands, provide the person with continuous real-time control over the robot, and create a communication vocabulary that can be extended for different tasks. Then once we can communicate with the robot, the next step will be how it knows what to do in a new situation. And we can again think of a spectrum of different approaches. On one side, we have artificial intelligence models that learn to be autonomous from large amounts of data or experience. And on the other side, we have robots that are directly controlled by a person. So in terms of robots from the movie Big Hero 6, this is like going from Baymax, who's a personal healthcare assistant turned superhero, to microbots that obey direct instructions from a user's brain signals. And for this thesis, we'll focus more on using the person in the loop to guide immediate behavior and to guide the learning process. This can help address the fact that it's challenging to collect a large amount of data for human-robot interaction. And it also helps create interfaces with simplified models that can still apply to many different situations. So in some sense, this blends these aspects of communication and adaptability. It allows the person to convey what they think would be useful for the robot to do while they're working with it, and it lets the robot infer insights from these interactions. And along these lines, we can articulate a few key goals that we'll talk about today. We'll want to work towards intuitive interactions by detecting a person's physical and cognitive states, and we want to do this unobtrusively so they don't need to alter their natural behavior too much. And we'll focus on using muscle and motion signals today, but we've also incorporated brain signals as well. Then we also want to make the interfaces more plug and play, so casual users and experts can both start working with robots quickly. On the software side, this will mean developing classification algorithms that reduce the amount of calibration and training data that a person needs to provide. And on the hardware side, this will mean using minimal sensing and reducing the computational costs as well. Then keeping all of this in mind, we can develop algorithms for continuous control and also learning frameworks. And this leads us to our last main question about what we envision for robots. Once we have good ways of communicating, what should we actually tell the robots to do? So we consider three main ways that we might want to interact with the robot. We may want like a robot minion that follows direct commands that we give it from a distance, or we may want more of a robot sidekick that works directly with us on a physical task. And finally, we may want a robot apprentice that can learn from our interactions to become more autonomous or provide more proactive assistance. And this thesis has developed systems to explore each of these different roles. So they include remote control and supervision, physical collaboration, and teaching by demonstration. And we'll just focus on the bottom two of these today. But first, I'll give a quick overview of the top three to give a sense of the type of interactions that we're interested in. So one project for supervision used both brain signals and muscle signals. We used the brain signals to unconsciously detect mistakes and the muscle signals to actively correct those mistakes. And in particular, we use EEG to detect brain signals, and we classify error-related potentials. These are generated unconsciously by the brain whenever we notice something going wrong, particularly if it's unexpected. And we also use EMG to detect muscle signals from the forearm, and then we classify left and right gestures at any time so that the person can correct the robot's behavior. So basically, if we detect this error-related potential when the robot starts moving, it stops and asks the person for help. Then the person can use the gestures to scroll through the targets and indicate the correct behavior. And we'll also look at extending this vocabulary to additional degrees of freedom. Then we can think about increasing the amount of interaction between the person and the robot by looking at a robot sidekick. And in this case, they work on a physical task together, and we detect biceps and triceps muscle activity using EMG. And we process these to estimate a continuous lifting set point. So the robot roughly copies your lifting motion, but then you can also use gestures to nudge the robot up or down. So this is sort of like how you might lift a couch or something else large with a friend. You both lift it together to keep it level, but then you can also hold it at different angles. And then finally, we can extend this knowledge transfer a bit more so that we can have the robot learn from these interactions. So this project looked at using intermittent human demonstrations, and the robot basically learns from self-supervision, constantly trying to grasp the bottle. But if it can't figure out how to do it, it will ask the person for help. So this incorporates intermittent human demonstrations to improve the robot's learning rate and keep the human's workload low. And we also use this framework to investigate aspects of team fluency, like how the person perceives the robot's skill as it learns. So all of these systems looked at implementing ways for the human to interact with the robot. And underlying all of these are components that address the questions of communication and adaptability that we discussed earlier. They build on each other to develop a vocabulary for communicating with the robot, and then construct learning frameworks so that the robot can address new situations. And we'll take a look at each of these by focusing on the applications for remote control and for teaching by demonstration. So we'll first look at starting this vocabulary with discrete gestures, and then we'll extend it to include more continuous motions as well. And we'll also look at methods of conveying expert knowledge about the task and incorporate this into a framework for teaching by demonstration. So to start off, we can detect discrete gestures and apply it to remote control. And there are a variety of approaches that have been used to detect gestures and that we can learn from. These include different modalities like cameras or wearables, and also different algorithmic approaches. These include probabilistic techniques like hidden Markov models, supervised learning like neural networks, or being focused on the person in the loop, such as using template matching or heuristics. And in keeping with the objectives we outlined earlier, we'll currently focus on using wearable sensors for muscle and motion signals. And we'll focus on making more plug-and-play interactions from both the hardware and the software perspectives. On the hardware side, we'll aim to leverage the benefits that we mentioned before, including not having the person set up sensors in the environment and detecting hand or joint motions without putting sensors on the hand or joints themselves. On the software side, we'll focus on not requiring training data or calibration routines from each new user. And for some gestures, we'll do this using supervised learning trained on previous users. And then we'll extend the vocabulary to more gestures without requiring data collection by combining unsupervised learning with expert knowledge. So to start off, we use EMG electrodes to detect muscle signals from the biceps, the triceps, and from the forearm. And the forearm device also includes an accelerometer and a gyroscope to detect motion. Then we define a suite of 8 gestures that can serve as motion primitives for controlling a robot or other devices. As an example, we'll look at controlling a drone. So the first gesture that we define is briefly stiffening the upper arm. And this is sort of like a cringe gesture that you might do when you see something going wrong. So we use this to stop the robot. Then squeezing the fist is similar to a grasping or a selection action. So we'll use it to move the robot forward. And briefly rotating the hand can cause the robot to turn. And finally, waving the hand left or right or up and down will cause the robot to have translational motions. And this is the same wrist flexion or extension gesture in both cases, but the hand orientation will determine which direction is being indicated. And we explore 2 types of gesture detection pipelines. The wrist motions are detected using a neural network trained on labeled data from previous users of the system. And this can be helpful for letting the system automatically determine important features. But it can also be hard to add new gestures to the vocabulary since you need to collect more training data for each one. So for all of the other gestures, we use an algorithm for clustering streaming data online. This doesn't need training data ahead of time, but it does use expert knowledge of the expected signal shapes. So let's take a closer look at how this works using the stiffening gesture as an example. So arm stiffness is high when both the biceps and the triceps are tense. So we can start off by multiplying these signals together. Then we can essentially detect the gesture by looking at when the signal is sufficiently high. But then the question becomes, how high is high enough? Because one challenge of using muscle signals is that their levels change a lot between subjects and over time. So we can't really just use a fixed threshold. So to address this, we developed a clustering algorithm that creates a dynamic threshold by fitting Gaussian mixture models to the streaming data. So for now, we specify that there should be 3 clusters in the model. These are meant to represent when the user is relaxed, when they're just making small motions or performing other task operations, or when they're really stiffening their arm for that gesture that we want to detect. And to let these clusters be adaptive, we refit the mixture model to the data a few times per second. But this can also become intractable if we need to remember and process all the data that we've ever seen. So we store a rolling history of data for each one of the clusters. And this limits the amount of stored data and the computation time, but it also keeps gestures in the history, even if they're only made once in a while. So this will allow us to cluster the unlabeled streaming data in real time. And then we can detect gestures by looking at when the new points are classified as the highest cluster in the model. And to get a better sense of how this works, we can watch the model update in response to some gestures. The left graph here will show the stiffness estimate of the upper arm in black. And the right graph shows the contents of those 3 rolling buffers, and they're overlaid with the current clusters that are identified by the model. So as we go, the algorithm will sort the streaming points on the left into the clusters on the right, and also adapt the cluster cutoffs. And we can mostly focus on the left graph, which will color points red when they're detected as the stiffening gesture. And at first, the system hasn't seen any examples of a gesture, so it thinks that these small arm motions might be stiffening. But once it sees even a single example of the actual gesture, the cluster thresholds can adjust and learn to separate the small movements from the gesture. So it essentially performs calibration online while the user is performing gestures and interacting with the robot. And we can use this to detect gestures without labeled training data and without significant calibration routines, as long as that detection pipeline can be cast as a dynamic thresholding problem. And then, of course, we can use this to actually control the robot. So in this case, when you stiffen your upper arm, the robot will stop and hover. And we can also use the same building block for the other gestures. For example, fist clenching can be detected in basically the same way, except that instead of multiplying biceps and triceps, we multiply inner and outer forearm muscles. And we can also use this to detect rotation gestures, but with a bit more pre-processing. This gesture is basically rotating the hand to one side and then returning to neutral. So we expect the angular velocity of the forearm to have 2 peaks of opposite sign. And we can make an indicator signal to highlight this shape by using a rolling buffer. At each time step, we split this buffer of the angular velocity in half, flip and negate 1/2, and then multiply them. I like to think of this as like a folded product, since we can visualize it as folding the buffer back on itself and then multiplying. And this result will be high when there are 2 velocity peaks of opposite sign centered around the middle of the buffer. Then we can pass this indicator to the online clustering algorithm and detect when it's high enough to indicate a gesture. So far, we've looked at using this clustering algorithm to detect gestures directly, but we can also use it to augment supervised learning. As an example, we can consider the wrist flexion and extension gestures. And we use a neural network to detect them, since it might be a bit harder to develop an indicator signal. And I won't go into too much detail about the neural network, but I'll mention 2 aspects of the training process that help make it plug and play and that help it detect gestures at any time. So one is that we only train on data from previous users of the system, and we use a clustering algorithm to select informative training examples. The algorithm looks to identify distinctive characteristics about how people tend to make gestures, and then selects examples that highlight these traits. Then once we have this set of training examples, we use data augmentation to help make the real-time predictions more stable. The network is going to be trained on time-locked examples, but during online operation, it will continuously output predictions on a rolling basis. So the data augmentation helps anticipate this. It shifts examples in time, and it guides the network towards being tolerant of off-center examples without being too lenient and creating false positives. So together, these training aspects help make the network a bit more plug and play and improves the real-time performance. But another challenge with classifying muscle signals, as we mentioned before, is that their level can change a lot between subjects and over time. So to accommodate this, we normalize the muscle signals in each classification buffer independently. But this also means that the network will be amplifying small, noisy signals when the person is just resting or making small motions. So in parallel with the network, we use the clustering algorithm to gauge the overall level of forearm activation. And when this indicates that the forearm is activated enough to reasonably indicate a gesture, then we can actually act on the neural network predictions. So putting these together, we can use the neural network and the clustering algorithm to detect wrist flexion and extension. And we can use the accelerometer to infer the arm orientation when the gesture is made, so we can indicate left and right or up and down. Then we evaluated these pipelines with 6 users in an open loop setting. So we had LEDs cue specific gestures at specific times, but there was no robot being controlled. And across all of these gestures, the individual classifiers averaged about 98% accuracy on 1,200 examples. And the performance was also pretty consistent across all of the subjects. Then we added the robot and let users make any gesture at any time to control it. And on the right is the confusion matrix for the rolling classifications, which indicate whether the robot moved in the correct direction in response to each gesture. And while the previous metrics looked at gesture detection pipelines independently, we now also impose a hierarchy among the gestures to make them mutually exclusive. So this makes controlling the robot a bit more smooth and reliable. And we can also consider this a bit more qualitatively by letting the users control the robot. So these gestures can be used in a variety of robot tasks or even with generic electronic devices. But as a demonstration, we allowed users to control a drone. And in total, it flew for 2 hours over the course of 25 sessions with the 6 different users. And this allowed us to evaluate that gesture detection pipelines during a closed loop teleoperation scenario. And overall, the drone correctly responded to about 82% of over 1,500 gestures. An analysis of the muscle signals also indicated that their levels did vary significantly throughout the experiments and between subjects, as we might expect. So this suggests that the clustering algorithm successfully adapted to the changing signal levels, despite not having dedicated calibration routines or per user training data. So this has built up a gesture vocabulary using muscle and motion signals. It uses a mix of supervised and unsupervised learning to detect gestures in a plug-and-play fashion. The neural network is trained on previous users, and then the clustering framework extends the vocabulary without extra labeled training data. And then together, this allows someone to quickly start controlling a robot, such as a drone. But we can also think about how the robot can learn from these interactions. And for this, we'll look at extending the vocabulary to continuous motions and then using it to teach by demonstration. So there will be 3 main phases to this approach. The person will first perform the task themselves in the demonstration phase, and then the apprenticeship phase will let the robot copy their motions while the person supervises it. Then after learning the correct path, the robot will convert it to a generalizable representation that allows it to tackle new scenarios. And there's been a lot of work on learning by demonstration, and there are typically 3 main phases: the actual demonstration, segmenting the observations and creating abstract representations, and finally generalizing. And some common approaches to performing the demonstration include directly moving the robot or watching a person do the task with motion capture or wearables. Then these observations are often segmented and abstracted using unsupervised learning, probabilistic methods, or tracking different properties of the person's behavior. And the approach that we'll present today combines a few of these concepts to merge the demonstration and segmentation phases. We'll use a wearable IMU to track motions, and we'll allow the person to provide segmentation information during the task by using EMG-based gestures. And we'll apply this to both arm motions and to walking motions, depending on what the task requires. And we'll also add an apprenticeship phase that lets the person correct learned trajectories by using the vocabulary that we discussed earlier. And finally, there's the generalization phase to adapt behavior to a new situation. And typical techniques include inferring constraints, constructing optimization problems, or using predictive models. We'll combine a few of these concepts by using a constraint library to represent a path as an abstract graph, then adapt this graph to the new situation, and then formulate an optimization problem to convert that abstraction back to a concrete trajectory. An example scenario that we'll be focusing on is routing a flexible cable around pegs. And this could represent a mock installation or assembly task in a factory. So we want the person to demonstrate the task while wearing even just a single sensor, and then have the robot mimic that task by performing the trajectory on its own. And we'll also insert an apprenticeship phase to let the person fine-tune the robot's behavior. And instead of just memorizing a path for a single scenario, the generalization phase will use that example as a template for new scenarios. So starting with the demonstration phase, we want to infer the person's hand trajectory from a wearable sensor on the forearm. And it's tempting to simply integrate the accelerometer readings to go from acceleration to displacement. But unfortunately, IMUs have a lot of drift and noise that make this very inaccurate even after just a few seconds. So to address this, we adapt the concept that's often used for estimating walking motions, It's called zero velocity updating. And the basic idea is to reset integration when we know the person is stationary. And instead of using footfalls, we'll incorporate user feedback to annotate stationary waypoints. So the person will squeeze their fist at waypoints that they want the robot to learn, and they'll remain briefly stationary during this gesture. Then we can use that gesture detection pipeline that we developed earlier to classify these fist gestures using the dynamic clustering. And then we only need to integrate the accelerometer readings between the gestures, which makes the estimation much more accurate. So this leverages the person in the loop to infer piecewise linear trajectories. And since it uses the user's annotations, this can work for the arm motions that we see here, as well as for walking tasks where the person walks in large outdoor areas. And we'll take a look at an example of that later on. But unfortunately, this can still be a bit inaccurate due to the noise and the drift and the sensor resolution of the IMU. So we can have the person perform the task multiple times to help get a better estimate. But there will be a lot of variation between these due to the processing pipeline, due to the inaccuracies that we mentioned before, and also if the fist gestures are detected at slightly different times to have different endpoints. And the user will also not perform the path exactly the same way twice. So we'll need a way to merge these different demonstrations into a single trajectory estimate. For this, we use an algorithm based on clustering. And we consider each motion of each demonstration and represent it as a 5D vector based on its spatial displacements and its normalized timing information. Then we apply k-means clustering to all of these individual motions, and we set the target number of clusters to be the median number of motions among the demonstrations. And to help filter the results a bit, we eliminate outliers from the clusters, and we also remove clusters that have too few points. But in the end, we can use the centroids of the clusters to represent merged motions, and then we can use these to reconstruct a merged trajectory. So this lets us combine multiple demonstrations into a more reliable estimate, even if the individual paths have different displacements, timings, or even numbers of waypoints. But one natural question from this is, how many demonstrations do we actually need to perform? And to answer this, we can look at how much the merged centroid of a motion moves when the person provides an extra demonstration. So basically, what is the impact of adding an extra demo? So we collected 15 demonstrations for each of 27 trajectories, and then we simulated what would happen if fewer demonstrations were performed. For example, we looked at all possible pairs of demonstrations, or all possible groups of 3 demos or 4 demos, and so on. And in each case, we pretended that those were the only demonstrations provided, and we ran that motion extraction and merging pipeline on it. Then we added one of the unused demonstrations and merged the augmented collection. And this graph represents how much the motion displacement changed when that extra demonstration was added. And the impact of the extra demo decreases, as we'd expect, and there's also diminishing returns. So after 5 demos, the upper quartile of marginal adjustment is always less than 10% of the motion's length. And after 10 demos, it's under 5%. So this suggests that about 5 to 10 demos might be a reasonable number. And for the remaining experiments, we asked subjects to do 7 demonstrations, which hopefully keeps their workload low while yielding stable motion estimates. So now we have a pipeline for estimating and merging trajectories from the IMU, but there is one final issue to address before the robot can replay it. Since the sensor is wearable, it only provides information about displacements relative to the sensor and the person. So as shown in the top here, we want to convert from axes that are relative to the sensor to axes that are relative to the task. And as an example, we can consider this blue estimated trajectory and use gray cylinders that represent the pegs. So this path is actually a pretty reasonable estimate for going around the pegs, but it's really rotated relative to the board. So we can fix this automatically using a few assumptions about the motion. First, we can estimate the direction of gravity at each of the waypoints where we know the person is briefly stationary. And then we can rotate the trajectory so that gravity points downwards. And we also know that the task is basically performed in a 2D plane. So we can find the best fit plane to the waypoints and rotate the trajectory so that that aligns with the board. And since we know that the person basically faces the board during the task, we can use a pose estimate of the arm to ensure that we have the correct orientation. So this gives us a way to infer the transformation from the sensor frame into the roll frame. And this completes that pipeline for estimating arm or walking trajectories by augmenting IMU data with in-task gestures detected from muscle signals. It allows the person to demonstrate a piecewise linear path a relatively small number of times, and then it merges and transforms the results to estimate their motion path. Now, since the results may still be a bit inaccurate, we can use the previous gesture vocabulary to let the person supervise and refine the robot during the apprenticeship phase. So the robot will basically perform the task by following that extracted trajectory while the person supervises. If the robot isn't headed to the correct position, the person can intervene and remotely control it using gestures. And after each intervention, the robot will update its stored trajectory with the new waypoint and propagate the adjustment to all future waypoints too, to reduce the number of gestures needed later on. Then once the person is satisfied, the robot can replay the waypoints without needing any interventions. So this completes the extraction pipeline that uses even a single wearable sensor to go from demonstrations to a refined trajectory. And we can evaluate this pipeline, and we use it on a variety of cable routing scenarios. Altogether, there were 27 trajectories and over 600 demonstrations, ranging from 3 to 12 waypoints and 1 to 7 pegs. Most of these were done by a single user, but we also had 5 subjects perform a subset of them to investigate the cross-user performance. And in terms of the motion segmentation, nearly all of the fist gestures were correctly identified across almost 3,800 waypoints. And all of the merged trajectories had the correct number of waypoints if at least 3 demonstrations were used. And in terms of motion estimation accuracy, we found that 83% of the trajectories needed no adjustments or just 1 motion adjustment for it to have the correct topology around the pegs. But users typically adjusted the path a bit more than strictly necessary to have more of a buffer distance between the robot and the pegs and to just improve the aesthetics of the trajectory. So the median number of interventions that the users implemented was 3, and there was a median of 3 gestures per intervention. So overall, this indicates that the pipeline produced trajectory estimates from the wearable sensor that only needed moderate amounts of adjustment. And the users were able to use the gesture vocabulary to remotely supervise the robot. And we'll talk about this a bit more later as well, but we can categorize each of these demonstrated scenarios to describe their high-level objective of what they're trying to do for the task. For example, they may want to weave around all of the pegs so that they rest on them when the string is pulled taut. They may want to weave around some of the pegs, but leave some of them for future operations. They may want to go around just the convex hull of all the pegs, or they may want to drape over some of the pegs. And these underlying goals and constraints aren't explicitly represented by the pipeline that we've used so far, but we can start to think about these implicit objectives when we want to tackle new situations in the next section. So for now, we have a pipeline that can demonstrate trajectories with user-defined segmentation, and it allows the person to interactively refine the path by using the gesture vocabulary. But a true apprentice combines their observations with past experience to tackle new situations. So we'd like the robot to do this too. A major challenge, though, is that there is very limited training data available, since it's tedious for the person to demonstrate many different examples. It's also a bit hard for the robot to explore paths on its own, since it may damage the environment, or it's also hard to explicitly articulate an objective that the robot can use to evaluate whether its behavior is even good or bad. So since these make it a bit challenging to leverage supervised learning or reinforcement learning, we develop an optimization pipeline that uses expert knowledge to generalize from a single demonstrated example. So the setup for this phase is that we have 1 demonstrated trajectory that the person has shown can accomplish the task. Then given a new set of pegs and a starting and ending position, we'd like the robot to generate a trajectory with similar behavior. In this case, basically weaving around all of the pegs. And we'll assume that the pegs are ordered to roughly indicate how the path should visit them during the task. This could be provided by the user or inferred with some heuristics. And to start off, we'll consider local behavior of the path around individual pegs or sets of pegs. And we'll map each peg in the new scenario to a peg in the old scenario that it can use as a template for how the path should behave around it. For each target peg, we'll map it to the input peg that's in the most similar relative position along a path that connects the pegs in the provided order. Then to describe how the path behaves around those pegs, we'll use a predefined constraint library. This allows the expert to specify behaviors that may be relevant to the expected task. The current implementation focuses on these cable routing scenarios that we've looked at. So it has classes of constraints that focus on the path as a whole, such as wrapping around the peg or looping around all pegs, or limiting how sharply the path can turn. It also has classes that focus on individual waypoints, like needing to be near a peg or far from all pegs. And finally, there are some that focus on path segments, like needing to pass near a peg, have a buffer distance to avoid collisions with pegs, or limiting the length of a segment. And each of the classes in this library specifies 3 types of rules. It can determine whether it applies to an existing scenario, it can generalize its parameters to a new scenario, and it can formulate it itself in a way that can be used during optimization. For example, the buffer class will decide whether a path always stays a certain distance away from the pegs to avoid collisions. And then it will parameterize that distance in terms of the overall scale of the scenario, so it can generalize to a new situation that may be larger or smaller. And in terms of formulating the constraints for optimization, a set of differential inequalities and constraint bounds can check whether a given path achieves the desired behavior. For example, the contain class that checks whether the path goes around a peg will use 2 inequalities that each check whether 2 cross products are the same sign. So this checks whether the peg is within the area that's swept out between the 2 path segments. And this is differentiable, so it can be used during gradient descent. So now that we have these rules, we can iteratively apply them to the input trajectory to systematically describe its behavior. Conceptually, this builds up a graph with waypoints and pegs as nodes and constraints as edges connecting them. For example, we have the trajectory in blue and the pegs in black here. And this red edge connecting this peg and waypoint indicates that there's a contain class that's active between those nodes. So the path should go around the peg at that waypoint. And constraints that are independent of pegs, like limiting the segment length, can be thought of as properties that are stored within the waypoint node. Then we can use this graph as a representation to approach the new situation. So we can combine it with the mapping between input and target pegs to iteratively infer a constraint graph for the target scenario. For example, we'll start with the first peg in the target scenario, and we see that it's linked to the first peg of the template scenario. Now, this input peg in the input scenario has a red contain constraint that's linked to an initial waypoint. So we'll add a waypoint to the new graph that has the same type of constraint edge. And then we can record that this new waypoint should copy the behavior of this input waypoint. And we can see what other constraints are on this one. In this case, it has some constraints that are independent of pegs. So we can copy them over to the new one directly. It also has this orange buffer constraint linking it to the second peg of the input scenario. So we can look for any pegs in the target scenario that are supposed to copy that second input peg. And we can add a corresponding buffer constraint. Then we can continue this process, starting with any pegs and waypoints that are near the region that we just visited by the new edge. So this essentially traverses the graph in a roughly depth-first pattern, and along the way, it determines the number of new waypoints needed and how they should relate to the pegs. And note that the waypoints are placed here for visualization purposes, but we don't actually have locations for them yet. For this, we can convert the graph into a constrained optimization problem. And we can use the generalization rules in the library to adapt parameters as needed. And we can use the specified formulations to extract a set of search-based bounds and differentiable inequalities that check whether the constraints are satisfied for a given set of waypoints. And the final ingredient will be an initial path guess of the waypoint positions. I won't go into too much detail about this, but the current implementation basically places each waypoint near pegs that they're linked to in the constraint graph. And finally, we can solve this nonlinear constrained optimization problem to generate waypoint positions that satisfy all of the inferred constraints. And this yields a trajectory that mimics the input behavior, such as weaving around the pegs. And then we can use this to tackle a lot of different new scenarios. For example, here we use that same single input example in blue to create trajectories around many different sets of pegs. And in each case, it seems to copy that desired behavior of weaving around the pegs so that the string would rest on all of them once it's pulled taut. But we'd like to be a bit more systematic about evaluating these to determine whether the outputs are correct in terms of the task being performed. And here is where those categories that we mentioned earlier can come in handy. So each category has a high-level task goal that the person was trying to accomplish, and it has rules for determining whether that goal is met by a given trajectory. And the first test that we apply this to is seeing whether the generalization provides robustness to having the pegs move just a little bit. For each input scenario, we move the pegs by a small amount. And the gray circles here represent the allowable regions that we used. Then we perform the generalization and see whether the new path meets that category's criteria for success. And we made 25 of these random perturbations for each of the inputs, and a few of the examples are shown here. There were 550 total pairwise generalizations that were created this way, and about 98% of them satisfied that category's criteria for success. And under 1% of them were infeasible for the optimization solver. Then we can also test whether the robot can generalize to entirely new sets of pegs, in addition to being robust to small peg motions. So each row here represents outputs from the single input example in that row. And each column uses the same set of target pegs to show that different behaviors can be achieved with different inputs. And there were over 500 of these pairwise generalizations, so over 1,000 total generalizations when combined with the perturbation trials. And about 98% of them satisfied the category's criteria for success. And to test feasibility, we had the robot perform all of the paths shown here, as well as 16 others for a total of 58 paths. And about 97% of them didn't need any apprenticeship adjustment, while the remaining ones needed just a few gestures to increase the buffer distance to pegs. So overall, these results indicate that the library and the algorithm were able to capture many of the goals and constraints that the user had implicitly embedded in their demonstration. If different goals or tasks need to be captured, though, then the constraint library would have to be extended. So this has developed a generalization algorithm that uses a library to represent a path as a constraint graph, and then it uses that graph as a template for the new scenario. The new graph is then converted to an optimization problem that solves for appropriate waypoints. And so far, we've been using this cable routing scenario as an example, but the framework can also apply to variations on this task or to other tasks altogether. And I'll just show a few examples of some tasks that we've applied this to so far. And one is applying it to collaborative tasks. So in this case, the person can teach the robot a path that ultimately lets them work with the robot to complete it. So it basically teaches the robot to become more of a sidekick. And in this case, the two people originally demonstrated the task, and then the robot inferred the trajectory that one of them had used. And since the wearable sensors don't impose workspace bounds, the system also works on large outdoor tasks. For example, here the person will rope off an area using caution tape. And the motion estimation pipeline works basically the same as it did on the arm motions, but with one main difference. The person makes 2 fist gestures at each waypoint, one when arriving at the waypoint and one just before leaving. This extra segmentation information allows us to only focus on the portions of the demo that contain walking. So this can help eliminate impact of the task operations on the IMU. And we can detect these segments using the frequency content of the accelerations. Then the apprenticeship phase works basically the same as it did before, with gestures driving the robot around the court instead of moving it in the 2D plane. And finally, the robot can perform the task in the autonomous phase. And the generalization pipeline could also apply here too. So for example, the person could demonstrate how to rope off a small area with just a few posts, and then the robot could infer how to rope off a much larger area with a more complex perimeter. And one final scenario that we tested is doing survey operations. So here the points of interest are places to visit and photograph instead of pegs or posts to drive around. And some of the points of interest could also be considered like obstacles. So the same constraint library that we discussed before can also apply to this task. In conclusion, we've explored a few ways in which this thesis aims to move towards more plug-and-play human-robot interaction. We focus on not requiring per-user training data or calibration routines, and on using wearable sensors to simplify the hardware and computational demands. And biosignals allow us to detect physical and cognitive states that are useful for allowing the person to guide robot behavior in a variety of situations. Working towards these goals, we developed a suite of classification and motion estimation algorithms to create a communication vocabulary. The supervised and unsupervised pipelines detect gestures at any time, and combining these with IMU readings can estimate continuous motions. We then incorporate expert knowledge and use these building blocks to implement learning frameworks. These allow the robot to learn from the person's demonstrations and corrections, and then generalize to new task configurations. And finally, we've used these algorithms to implement multiple systems that evaluate their capabilities and user interfaces. These explore remote control, physical collaboration, and teaching by demonstration. Basically, they allow the robot to act as a minion, a sidekick, or an apprentice. And this helps move closer towards the goal of ubiquitous robots that could increase our capabilities and quality of life. And I look forward to seeing what new possibilities are unlocked as robot assistants continue to become more commonplace for a wider population of people. So this thesis would not have been possible without all of the amazing people that I've been able to work with. And first and foremost, I want to thank Daniela. You've really shaped how I approach research and how I think about robotics in so many ways. Your inspiring visions of how robots can improve our lives always remind us that what we do can have a positive impact on society. And beyond that, you go to great lengths to make sure that everyone in the lab is excited about what they're working on and excited about doing it together. I really appreciate the flexibility about what directions we pursue and the community that you've created. And I'd also like to thank my thesis committee, Julie, Randy, and Peter. Julie, it's been a pleasure to learn from you in so many different contexts over the years, including your mentorship as heads of house in SP, being a TA for you, and now as part of my committee. I really appreciate all of your guidance and support. And Randy, thank you for all of the research advice, both during the RQE and now for the thesis itself. Your insightful questions always help probe the underlying issues and give them higher level context. And Peter, thank you for starting me on this path by introducing me to robotics research all those years ago as an undergrad at Columbia. I appreciate the opportunities and the support that you provided and that you continue to provide now as you help to improve my thesis. And I'd like to thank my collaborators, Andres, Steph, and Raman. You helped develop the system for using EEG to supervise robots. So thank you, Andres, in particular, for introducing me to user studies and for showing me the value of always having some bad jokes on hand to entertain subjects. And Steph, thank you for all of your help on this project, as well as all of the other projects that we've been able to work on together, including our many Ubayadi adventures. And Raman, Jeff, Lindsay, and Chris all helped explore ways to incorporate more machine learning into these interaction pipelines. And I've also really enjoyed getting to learn about aspects of soft robotics by working with Robert and Cheng-Hoon and Bianca. And I'd also like to thank the amazing CSAIL staff for all of their support. I'll give a few shout outs in particular to the communications team, including Rachel, Adam, and Tom, and to Ron and to Mike. Without them, our work would be seen by much fewer people. The demo rigs that I created for these projects would not have been possible, and our lab would run much less smoothly. And beyond just working together, our lab has had a lot of fun adventures over the years. From biking or go-karting to scuba diving and making fake rock bands, I'm grateful for the welcoming community of the DRL and for the friends that I've met there. I also really appreciate the support of friends from all of the communities that I've been fortunate to interact with. Shout outs to Trevor, Alex, and Danny, to the JJ8 crew, including Kelvin, Rose, Mark, and Brandon, and to Mike, Nathan, Ottman, Miguel, and Leonard. And a huge thank you to everyone that has made Sydney Pacific the amazing graduate community that it is. When I first got involved in the student government there, I had no idea the path it would set me on and the wonderful people that I would meet. So thank you to our intrepid heads of house, Julie and Neil, Alberto and Nuria, to all of Spec 15, to Arco and Sydney and all of the trustees, to all of the officers I've been able to work with, and to everyone else that makes SP so much more than just a place to live. And of course, I wouldn't be here without my wonderful family. To my parents, Barbara and Jeff, to Alexis and Danny, to Pete and Mary, Michael and Teresa and Mike, your unconditional support means so much to me. Not to mention all of the fun antics that we always get up to whenever we meet. I'm really glad we've gotten to keep in touch even more than usual during the last year, and I hope that we can continue this moving forward. Thank you also to all of the Grays. I really look forward to the next time we get together so that we can finally have that bocce ball rematch. And thank you to Rhonda, Fred, and Alec. I'm glad we've gotten to spend so much more time together lately, and I really appreciate everything that you've done to help make this possible. And finally, thank you to Sydney. Your support is unwavering, your enthusiasm is infectious, and you never cease to inspire me. Every day is an adventure, and I can't wait to see where it takes us next. And because of all these people, I have this thesis that I've presented today, and I'd be happy to continue chatting more. Thank you.
Thank you. Thank you so much, Joseph. So I see that some of us are in our conference room, but I stayed in my office. So I will join the people in the conference room a little bit later. Let me tell you what's going to happen next. First of all, I forgot to introduce the thesis committee of Joseph. So the committee includes Professor Randy Davis and Professor Julie Shah from MIT and Professor Peter Allen from Columbia University. And the next part of the defense will actually be done in two pieces. First, we will take questions from the general audience, and then Joseph will have a closed session with the committee. Are there any questions from the general audience? I can't see the room. Anybody has any questions in Kiva or online? Please put your hand up, your yellow hand up, or come forward. Don't be shy. Okay, somebody's coming forward. Excellent.
Hi, Joseph. I'm going to ask a stupid machine learning question. Did you try just using neural networks and see if that works?
So we did use neural networks for some of the gestures, like for the left and right gestures, and that did work pretty well, even with a relatively simple neural network. And we did make some modifications to make it more plug and play and real-time reliable. But then we thought about using that for other gestures as well. But one of the issues is that then we would need to collect a lot of training data from all of the users for each new gesture pipeline that we want to add. Or we'd have to have one neural network for all of the gestures and retrain that every time we add a new gesture. So we wanted to explore this unsupervised learning pipeline that helps streamline that process. But I would definitely be open to incorporating more neural networks in the future.
Cool, thank you.
Thanks, Lucas. Anybody else? Okay, there is Steph. Go ahead, Steph.
Hey, Joseph.
Hi, Steph.
I have a kind of a basic question. What did you find to be the most difficult part with the classification?
So I think in general, the signals just vary a lot between subjects. So allowing it to have cross-user performance without training a lot on each new user is one of the most challenging aspects.
Mike?
Hey, Joseph. So my question comes from the industrial perspective of how painful was it to work with the robotics vendors when it came to setting things up, or was it straightforward?
That's a great question. So in our case, we basically used commercially available products for the robots and for the sensors. So we didn't really need to make modifications to those. So we didn't need to work with the hardware vendors directly. So we used Baxter Robot from Rethink Robotics, and we also used the Stretch Robot from Hello Robot, and we used the Myo armband. And these could all be sort of switched out depending on the task and what you need to accomplish.
Thanks.
Yep.
Okay, one more question. Robert.
Hello.
Hi, Robert.
Awesome presentation. Hello. I had to wait for a second. I had to put my son to sleep, but he's sleeping now. I have a question for you, going back to, if you were to reimagine this thesis from the beginning again, what would you have done differently in terms of how you approach this? What would you like give a first year student sort of as an advice of like how you should approach this problem completely differently, or are you very happy with the way you approached it?
I think in general, I'm happy with the way we approached it, but there's sort of two sides to doing that, right? You can either go a bit more bottom up and think of the gesture vocabulary and then think about what you can do with it, or you can go more top down, thinking about what you want the robot to generalize to, and then what building blocks you'll need to implement that. So I had started more on the gesture vocabulary side, but I think starting on the learning and generalization side could also be very valuable. So I think it would be interesting to extend this to more customization, for example, to allow the person to define their own gestures and to have more task knowledge embedded in the higher level so that the robot can infer what to do based on those gestures.
Thank you.
Well, it's good to see so many of you at this presentation. I'm so happy to see some of our alumni who have returned in addition to everyone else. If there are no further questions, then I suggest we go to the private session with the committee. Joseph, can you send us to a breakout room, or how should we do this?
Yes.
And then let's see. This is the thesis defense date in a day in our group. We have 3 PhD defenses today. We have Lucas's defense coming up. We had Andy's defense in the morning. Those of us who are in Boston, we will gather together in the amphitheater at 4:30.
So I just opened up the breakout room, so hopefully you've received.
So we will return after the meeting with the committee for those of you who wish to stay. We just wanted to say congratulations. You have done a wonderful PhD thesis, and we are very proud of all that you have achieved. So congratulations on passing, Joseph.
Thank you.
Great job, Joe.
Yay!